Hello friends, in this video we will talk about a concept called free body diagram, or in short it is simply called FBD. Okay, so I have divided this lecture in few topics. First of all, we will quickly study what is the Newton's third law of motion. Then we'll jump on to our topic, that is what is an free body diagram. Then we will learn how to draw an FBD, and here we will see some illustrations as well. And at last we will do some numericals. Okay, so this will be the sequence of this lecture. So let's begin. Okay, let us discuss the Newton's third law of motion. Newton's third law of motion. So what does this law say? To every action there is always an equal and opposite reaction. And this action and reaction are nothing but forces. Or simply we can say that forces always occur in pairs. Okay, they always occur in pairs, and these pairs are known as action-reaction pairs. Okay. One more thing we will discuss here is the normal force. What is a normal force? Normal force. It is simply the perpendicular component of the contact force. Okay. And what is the parallel component of contact force? The friction. Okay. Now let us proceed further. So now we'll come to our topic, that is what is an free body diagram, FBD. Okay, so FBD is simply a tool in mechanics which is used to solve complex problems. What are complex problems? Those problems involving more than one particles. Okay, these are complex problems. And how do we do that? We just divide a bigger system into smaller ones, and use Newton's laws of motions on it. And what is the application of this FBD? It is used to calculate unknown forces, in a system. Okay, so let us revise quickly. What is a free body diagram? It is a tool in mechanics which is used to solve complex problems. What are complex problems? Which involves more than one particles. And how do we do that? We divide a bigger system into a smaller system and use Newton's laws of motion on each of these systems. And what is the application of this FBD? It is used to calculate unknown forces in a system. Okay, now let us learn how to draw an FBD using some illustration. So the next subtopic is how to draw a free body diagram. Okay, so there are few steps involved while drawing a free body diagram. The first one is that Draw a complete schematic diagram of the problem. That is, draw a complete schematic diagram of the problem. What is a schematic diagram? In which all the forces, components, etc. are shown. Components like hinges, supports, etc. So everything will be shown in this diagram. The second step will be choose any part of the system as the smaller system. That is, choose any part of this diagram, of the above drawn diagram, as one system. Okay, and then for this chosen system, draw another diagram in which all the forces along with their magnitude and direction is shown. And for the unknown forces, we will specify the direction logically. Okay, we will see how. So let us take an example. Suppose there is a table. This is a table, and there is a book resting on this table. This is the book. Okay, so we will draw the free body diagram for both the table and the book. Okay, so first of all, let us take this book. Okay, here I am drawing it. This is the book. Okay, so what will be the forces which are acting on this book? First of all, suppose the mass of this book is m, small m. So there will be first of all a weight acting downwards, which is equal to mg. And since the book is resting on this table and both are at rest, so there will be a normal force provided by the table to the book. So there will be a normal force provided by the table. Let us call it as m. Now since and the book is at rest, that means the net force will be equal to 0 on this system. This is our system, the smaller system. Okay, F net is equal to 0. That means n minus mg will be equal to 0. That implies the normal force will be equal to mg. Okay. Now here's one thing which you need to note over here. Though the normal force and the weight of the book are equal in magnitude and opposite in direction, but they are acting on the same body, on this book. So they do not constitute an action-reaction pair. Why? Because we have just studied about that action-reaction pair occurs on two different bodies, not on the single body. Here it is a single body. Although they satisfy the other two conditions, that they are equal in magnitude and opposite in direction, but they are not action-reaction pairs. Okay, this is something to be noted over here. Now let us take another illustration. Suppose the table and the book are resting or are placed inside a lift, an elevator, what you can say. So suppose this is the elevator, the lift. Okay, and this is the table inside it, and on the top of the table this is our book. Okay, now suppose this elevator is accelerating upwards with an acceleration equal to g by 2. So the acceleration of the table will also be g by 2, and for the book it is also G by 2. Okay. Now we will do the free body diagram for both of these book and table again. So let us draw first for the book. So this is our book. What are the forces acting on it? First of all, the weight of the book acting downwards, mg, and the normal which is provided by the table in the upward direction. This is n. Okay. And we know that the acceleration of the book is upward and the value is equal to G by 2. That means the normal must be greater than the weight of the book to provide this acceleration. So how do we write that? N minus mg will be equal to the mass times acceleration of the book. This is nothing but the second law of motion. What is the second law of motion? Force equal to mass times acceleration. Force net. Okay, this is the Newton's second law of motion. So this is our equation. Rewriting it again, n minus mg will be equal to m times, what is the acceleration? G by 2. Okay. That means the normal reaction is equal to mg by 2 plus mg, which is equal to 3 by 2 mg. This is the normal reaction on the book by the table. Okay. Now let us consider the table. So this is our table. So what are the forces acting on this table? First of all, according to the Newton's third law of motion, for every action there is always equal and opposite reaction. So the table was exerting a force equal to the n on the book. So the book will also exert the same force but in the opposite direction on the table. So there will be a normal force acting on this table in the downward direction. Now suppose the weight of this table is capital M. So the weight will act also in the downward direction and the magnitude will be equal to capital M G. Okay. Now since the table is moving upward or accelerating upward with the lift with an acceleration of G by 2 in the upward direction, the floor of the lift, which is in contact over this space, both of these legs of the table, will exert a force which is called as normal force, which will be the normal force provided by the lift on this table. Let us call it as n dash. Okay. So the net force on the table will be equal to F net will be equal to, since the direction is in upward direction, that means the n dash must be greater than the sum of these two. So the F net will be equal to n dash minus n plus mg. Okay, this is the net force, and this must be equal to the mass times acceleration of the table. This must be equal to the mass of the table, which is equal to m, times this times the acceleration of the table equal to G by 2. Okay, that means n dash will be equal to mg by 2 plus n plus mg. We have just calculated n as 3 by 2 mg. That means n dash will be equal to mg by 2 plus 3 by 2 mg plus capital Mg, which is equal to 3 by 2 g m plus m. This is the normal reaction on the table by the lift. Okay. So what we have calculated? We have calculated first the normal reaction, the normal force on the book by the table, and second we calculated the normal force on the table by the lift using the free body diagrams of both the books and the table. Okay, so I hope the concept of this free body diagram is clear to you now. Now let us solve some examples using the same concept of free body diagrams. Okay, so here's the question. What does it says? A block of mass 10 kg is kept on a rough inclined plane as shown in the figure. This is the figure. A force of 3 Newton is applied on the block. The coefficient of static friction between the plane and the block is 0.6. What should be the minimum value of force F such that the block does not move downward? Okay, so what we have given the coefficient of static friction mu s equal to 0.6. Okay, now first of all let us make the free body diagram of this block. Let us make the free body diagram for this block. So suppose this is the block. First of all, there will be a weight of this block acting in the downward direction equal to mg. This is the angle of the slope equal to 45 degrees. Okay. This is the force F which we need to apply. Also, since the block wants to move downward, there will be a force of friction acting in the upward direction which is equal to Fs. So there will be a force of friction in the upward direction. Also, the block and the inclined surface are in contact, so there will be a normal force acting on the block. So there will be a normal force, let us call it as N. Now if we resolve this weight into two directions, we will get the component along the normal direction equal to, this angle will be 45 degree, so this will be equal to mg cos 45 degrees, and along the plane it will be equal to mg sin 45 degrees, plus there is one more force acting in the along the plane which is equal to 3 Newton. So one more force, 3 Newton. Okay, so this is the free body diagram for this block. Now just rewrite the equations. First of all, write for the normal direction. So what are the forces we have in the normal direction? First is this normal force, and second is the component of the weight along this normal force. Now since the block is not moving in this direction, in this normal direction, the net force in the normal direction must be 0. That is the sum of all the forces in the normal direction must be equal to 0. That means N minus mg cos 45 will be equal to 0. That means N equals mg cos 45. M is given as 10, G will take as 10, cos 45 1 by root 2. So the normal force N will be equal to 100 by root 2. Okay, newtons. Now let us talk about the forces in the inclined direction. So what are those forces? The force which F which we need to apply, the frictional force, mg sin 45 and 3 Newton. First of all, calculate this frictional force. So the static friction Fs is given by mu s times the normal reaction. Mu s is given as 0.6 and we just calculated as 100 by root 2. So this will be equal to, the static friction will be equal to 60 by root 2. Okay, in newtons. Now let us write the equation for the inclined components. What we have, F plus Fs, F plus Fs is equal to mg sin 45 degrees plus 3. Okay, Why we created this? Because we want to just stop the motion of the block. Okay, we do not want it to move either upwards or downwards. We just want it to stay where it is. Okay, so that's why we created this left hand side to right hand side. Now we just calculated the friction force as 60 root 2. So F plus 60 by root 2 is equal to M is 10, G is also 10, sin 45 is equal to 1 by root 2 plus 3. That means F is equal to 100 at root 2 plus 3 minus 60 by root 2, which is equal to 3 plus 40 by root 2. Okay. So F will be equal to 3 plus 20 root 2, which is nearly equal to 32 newtons. Okay. So this is the force which we need to apply in the upward direction of the slope so that the block will remain at rest. Okay, so this is the answer for this question. So I hope the concept of free body diagram is clear to you. Thanks for watching.